to an excited state. Okay, and this is the famous Lipgier color wheel, which was discovered by Sir Isaac Newton in the year 1666. And normally, in terms of any compound, what we normally see is a complementary color. Okay? For example, and this is the famous material absorbed color violet, which was discovered by what we normally Newton in the year going to be yellow in the year 1666. Compound and normally the color would be red compound. That does not we normally see that a complementary color. Okay. For example, and this is the famous material absorbed color violet. It can have a discovered color what we normally see in the year short line, but a very in the year 1666. Usually overlaps over a range normally the color would be red compound. Whichever not we normally see that we get complementary color. Okay. For example, and this is the famous material. Please remember color violet can have a discovered color what we normally see in the year short line. But in the year usually overlaps over a range normally the color would be red compound. Whichever not we normally see that we get complementary, etc. For example, and this is the famous material. Please remember color violet can have a discovered color what we normally see in the year short line. All of them in the year usually overlaps over a range normally the color would be red compound. Whichever not we normally see that we get complementary. For example, and this is the famous material. Please remember all of them usually overlaps normally complementary. For example, and this is famous all of them usually overlaps normally oxidation of manganese 3 plus into manganese 5 plus. And manganese 5 plus is extremely happy to stabilize as a tetrahedral coordination. So the trigonal bipyramidal coordination changed into a tetrahedral coordination. The compound gives a kind of the greenish blue colored oxidation of manganese 3 plus into manganese 5 plus. I'll come back and address manganese 5 plus is extremely happy later to stabilize as a tetrahedral coordination. So the trigonal bipyramidal coordination changed into a tetrahedral coordination. Then the compound gives a kind of the greenish blue colored oxidation of manganese 3 plus into manganese 5 plus. I'll come back and address manganese 5 plus is extremely happy later to stabilize as a tetrahedral coordination. So the trigonal bipyramidal coordination changed into a tetrahedral coordination. Then the compound gives a kind of the greenish blue colored of manganese 3 plus into manganese 5 plus. I'll come back and address manganese 5 plus extremely happy later to stabilize as a tetrahedral coordination. So the trigonal bipyramidal coordination changed into a tetrahedral coordination. Then the compound gives unfortunately, the most stable phase is yttrium gallium oxide, which is a garnet structure, which is also an excellent laser host, YAG laser. Okay, when you have a yttrium indium oxide, this is a YIG laser. Yttrium gallium would be a YAG laser. But we eventually arrived at the most stable phase, interesting solution route, yttrium gallium oxide, garnet structure, which is also an excellent laser, and eventually prepared the laser. When we look at a compound indium oxide, as is seen here, you see a very gallium deep purple color. But we eventually arrived at the most stable phase, very solution route, gallium oxide, garnet structure, which is also an excellent laser, eventually the gallium. When we look at a compound indium manganese is seen here, you see a very deep purple color. But we eventually arrived at the most stable phase, very solution from blue gallium oxide, garnet structure, we get a very interesting eventually the gallium. When we look at a compound indium manganese is seen here, you see a very gallium. But we eventually arrived at the most stable phase, very solution from blue gallium garnet structure, we get a very interesting eventually the gallium. When we look at a compound manganese is seen here, we see a very but we eventually arrived at the most stable phase, very solution from blue gallium garnet structure, we get a very eventually the gallium. When we look at a compound manganese is seen here, but we eventually arrived at the most stable not only you have an attractive colored compound, but it also reflects the heat back into the atmosphere so that the building is remaining cool, and these are known as the cool pigments. Okay, now coming back to that, we started exploring, looking at different types. Not only have an attractive colored because in solid state chemistry, if you want to develop something new, so that the building is remaining cool, and these you look at known as the cool. So these are very well established. You look for any property. Coming back to that, we started exploring. There are other minerals. Looking at different minerals, not only have an attractive color, because in solid state chemistry, and you want to develop something new, so that the building is remaining cool, and these remember are known as cool. So these are very well established now for any property. Coming back to that, we started exploring. There are other looking at different minerals, not only have an attractive color, because in solid state chemistry, and you want to develop something new, so that the building is remaining cool, and these remember are known as cool. So these are very well established. This particular compound, coming back to that, we started exploring. There are other looking at different minerals, not only have an attractive color, because in solid state chemistry, and you want to develop something new, so that the building is remaining cool, and these remember are known as cool. So these are very well established. This particular compound, coming back to that, we started exploring. There are other different minerals, not only have an attractive color, because in solid state chemistry, and you want to never examine, so that the building is remaining cool, and these remember are known as cool. So these are very well established. This particular compound, coming back to that, we started exploring. There are other distortion minerals, not only have an attractive color, because in solid state chemistry, and you want to never examine, so that the building is remaining cool, and these remember are known as cool. So these are very well established. This particular compound, coming back to that, we started exploring. There are other distortion minerals, not only have an attractive color, because in solid state chemistry, and you want to never examine, so that the building is remaining cool, and these remember are known as cool. So these are very well established. This particular compound, coming back to that, we started exploring. There are other distortion minerals, not only have an attractive color, because in solid state chemistry, and you want to never examine, so that the building is remaining cool, and these remember are known as cool. So these are very well established. This particular compound, coming back to that, we started exploring. There are other distortion minerals, not only have an attractive color, because in solid state chemistry, and you want to never examine, so that the building is remaining cool, and these remember are known as cool. So these are very well established. This particular compound, coming back to that, we started exploring. There are other distortion minerals, not only have an attractive color, because in solid state chemistry, and you want to never
published in 2005, you have a gold nanoparticle kept at a fixed distance from a dye molecule, and the spacer used was double-stranded DNA whose length you can vary, and then you study the rate as a function of the distance of the dye from the nanoparticle, and it was found that it is not 1 by distance to the power of 6, but it was 1 by distance to the power of 4. So this is actually very interesting, and in fact they observed transfer not up to 100 angstroms but up to 250 angstroms. And so this was actually a very fascinating experimental observation. So we decided to try to understand this process. So in the case of a nanoparticle, these are metallic nanoparticles. You can have excitations of the nanoparticle which are actually plasmons, right? So you have plasmons, and you also have excitations which are referred to as electron hole pairs. Plasmons are actually excitations of a large number of electrons, while electron hole pairs are only excitations of single electrons. So this interaction, the electrostatic interaction between the excited dye and the nanoparticle causes a plasmonic excitation or electron hole pair excitation in the nanoparticle. So that is the mechanism of energy transfer, and the question was what would be the distance dependence? Would it be distance to the power of -4? To arrive at a conclusion, we used what is referred to as the jelly model for the nanoparticle, and the rate was actually calculated using what is known as the Fermi-Gordon rule. I will not go into the details of the calculation, which are of interest only to a quantum chemist. So let me just tell you the result. You see, there are different modes of the nanoparticle. You have what is referred to as the dipolar mode, and this blue line actually shows the distance dependence of the energy transfer to the dipolar mode. So energy is transferred from the dye to the dipolar plasmon or dipolar oscillations of the nanoparticle, and there the distance dependence actually would be 1 by r to the power of 6. You have the dipolar, and then you have quadrupolar. Here the distance dependence is different, and it is given by this magenta line, and then you have what is referred to as the hexapolar. There again the distance dependence is different, but the dominant one as far as the rate is concerned is the dipolar mode. And for the dipolar mode, actually the distance dependence is 1 by r to the power of 6. For quadrupolar, it is 1 by r to the power of 8. And for the hexapolar, it was 1 by r to the power of 10. So therefore, you see that at all distances, it is only the dipolar mode, and therefore the distance dependence that we theoretically found was only r to the power of -6. We did not find d to the power of distance to the power of -4. So the result, because I would likely to run out of time, I am not giving you details, but what we essentially found was that the distance dependence was the traditional expected distance dependence. It is r to the power of -6, and short distances there are corrections because you can have the quadrupolar or hexapolar modes contributing, and their distance dependence will be r to the power of -8 or r to the power of -10. And in fact, we concluded that plasmons and electron hole pairs do not give distance to the power of -4. So we thought of other possibilities. For example, can the energy be transferred to the DNA? Or maybe what we have done is we have assumed that the nanoparticle is completely spherical, but actually it is not. It is not a sphere. Can that be the reason? And we analyzed these things carefully and concluded that these are not responsible for the observed distance dependence. So therefore, we have not been able to arrive at an explanation of the results of Strauss et al. But of course, you see, this is a negative result in that sense, but we did publish this, and till today, this was published about 10 years ago, 12 years ago, and till today, the Strauss et al. Have never written anything contradicting our finding. So, I mean, if you ask me, I would say that we are right. And then, of course, you see, if it is distance to the power of you need an explanation as to what is responsible, and there is no explanation that is available now. So therefore, I personally have come to the conclusion that I don't believe the experimental results. So, but then of course, you see, nobody likes to write a paper saying that an experiment is wrong. If possible, you would like to say that, okay, this is in agreement with the experiment, but that is not what happened. So that left us a little bit unhappy, and then we said, okay, if there is no distance to the power of -4 in this system, can one think of other systems where the rate is proportional to distance to the power of -4? And then immediately we thought of graphene. So we said, okay, you have graphene sheet here. Graphene, of course, is very well known these days. And imagine you have a sheet of graphene and you keep a dye molecule at a particular distance, which we denote as Z, and then excite it. Naturally, energy is going to be transferred to graphene. And what would be the distance dependence was the question that we asked, and we had some simple reasoning to convince us that this will be very interesting because we expect it to be distance to the power of -4. So we performed very simple calculations to find the distance dependence. Actually, the calculation, I have to confess, is very crude. It is essentially a chemical molecular orbit type calculation which takes into account the pi orbitals of the system. But the nice thing is that it is possible for us to get analytical results. You don't even need a huge computer, right? You can do the calculation using just pen, paper and pencil, which is what we did. And our results are actually valid at large distances. It will break down. We know that it will break down when the distance is closer than 10 angstroms. For distances closer than 10 angstroms, one has to do a better basis set and so on. It will need a heavy computing. And usually I hesitate from doing heavy computations, and therefore we left it at that. But later on, after we published our results, other groups have done it and verified our results as well as obtained results at closer distance. So the idea is actually very simple. You have a dimensional sheet of graphene shown here, and these are this is the pi system of graphene, and the orbitals, the p type p orbitals, unhybridized p orbitals are shown there, not all of them, but some of them. And these are actually delocalized over the entire system, which is infinite in 2 dimensions. And so therefore what will happen, they will overlap to form molecular orbitals, and the energies between these molecular orbitals will be very small. Essentially, the energies form a continuum. So therefore, you have what are referred to as the energy bands of the system. And if you want to characterize a particular molecular orbital, what you can do is you can use wave vector, which is actually equivalent to momentum of the electron in the 2 directions. So that's why you will see this is a vector. And so the wave function is characterized by a 2-dimensional wave vector, and you can then get the energy, which is a function of this 2-dimensional wave vector k. And here is what is referred to as the energy bands of the system. So if we plotted the allowed energy levels of the system as a function of the wave vector, the energy is along the vertical axis and the 2-dimensional wave vector is along the horizontal axis. And then what you get is actually you get something like the bonding and anti-bonding molecular orbitals. You get energy essentially 2 bands. The lower one is the valence band and the upper one is the conduction band. In the ground state, only the lower band is completely occupied, so each molecular orbital has 2 electrons, and the conduction band is empty, and these bands actually meet at points which are referred to as the K points. And the structure of this plot near the K point is very interesting, because if you took this and magnified it, you will find 2 cones which touch each other. And this is the major, these are actually referred to as the Dirac cones, and this is the reason why the physicists are so much excited about graphene. So if you think of the process of energy transfer, what happens is that you have a dye molecule, you excite it as a transition dipole in the excited state, and that transition dipole has its electrostatic interaction with the electrons of the molecular orbitals of graphene. And as a result, what happens, that is what is shown here, this dye molecule, it is excited, so there is 1 electron in the LUMO and 1 electron in the HOMO. And this electron interacts with the electrons of graphene, which are shown here. The energy levels of graphene form a continuum. and all the levels up to the Fermi level are occupied with 2 electrons. So there is electrostatic interaction between this excited electron and an electron of graphene, and what happens, energy is transferred from this electron, it will come down and the electron on graphene will go up. So that is what you are going to see now as an animation, and this is what has happened. So if you see an electron having a wave vector k was promoted and it has gone to a wave function or a molecular orbital having a wave vector k plus q, and we normally say that this is an excitation of wave vector q because there is a change in the wave vector by an amount equal to q. So we say this is excitation of wave vector q, and that is the process, and I would like to calculate the rate of this process. This is another way of representing the energy bands of graphene. Actually, earlier picture you had seen two cones, but now instead of drawing a cone, I have just drawn a two-dimensional version of it. So this is the lower cone, the valence band, and that is the upper cone, which is the conduction band, and here is the Fermi level. Now, so if you imagine exciting an electron from the valence band to the conduction band, you see you can have an excitation of this sort, which is a vertical line, and because it is a vertical line, the horizontal axis is actually the wave vector, so this means that there is no change in the wave vector, which essentially means that the value of q is equal to 0. Or you can have excitations with which are not represented as vertical lines. These would have a change in the wave vector, and that would have a non-zero value for q. These are actually important, and that is the reason why I stress these. So again, let me skip a lot of algebra and tell you the expression for the rate. The expression for the rate is an integral over all possible wave vectors. Why you have to integrate over all possible wave vectors? The answer is that you have large number of excitations possible, and you have to sum over all the possible excitations. And what is the quantity that you have to sum over? Well, the quantity is interesting. You have exponential of e to the power of minus 2q. Q is the magnitude of the wave vector q. And Z in here, remember, is the distance of the dye from the graphene sheet. So the Z is the important quantity. H cross omega is the excitation energy of the dye molecule, and Vf is a quantity which is referred to as the Fermi velocity of graphene. So this integral, I mean, you cannot do it analytically, but if you can do it analytically in certain condition. If Z is very large, you can argue, I mean, if you are good in mathematics, you can very easily see this. You can argue that this integral will reduce to 1 by Z to the power of 4, and therefore the rate is proportional to 1 by Z to the power of 4. As I said, we had anticipated this by some very simple arguments, but here is a rigorous calculation showing that there is this true. So therefore it has a power law dependence, and in fact, why do you have this 1 by Z to the power of 4? The answer is that it is the excitations having small changes in the wave vector. So small q is actually leading to 1 by Z to the power of 4. So if you did not allow these small q excitations, then you will not get 1 by Z to the power of 4 dependence, and this again is important because we will make use of it. So then, of course, you can calculate the rate. Logarithm of the rate can be plotted against the distance, and against logarithm of the distance, and you will get a straight line. The slope is minus 4, showing that it is distance to the power of minus 4. And further, we did calculations for pyrene, and we found that quenching an excited pyrene molecule can be quenched by graphene even up to a distance of 30 nanometers. Whereas traditionally you would have expected that it is only quenching will take place only up to 10 nanometers. So for graphene, the quenching takes place up to 30 nanometers, which is very interesting. And further, graphene has another very interesting property. It is a universal acceptor. You see, normally when you have a donor and an acceptor, you have to match them so that the energies of the two match. Excitation energy of the donor has to be matched by the excitation energy of the acceptor. Then only energy transfer will take place. But in the case of graphene, what happens is that whatever be your donor molecule, graphene has a continuum of excitations, and therefore it has a corresponding excitation which matches with the energy of the of the donor, and therefore graphene is a universal acceptor. So we did all these calculations and pointed this out and published a paper. But of course, you see, we were looking for experimental results. There was none available. And then we tried to persuade experimentalists to do the experiment, but then we were not successful. So eventually I gave up. And I found consolation in this rather famous statement made by Einstein. A theory is something that nobody believes except the person who made it. Our theory was actually crude, and so people did not probably believe it. In comparison, if you think of an experiment, it is something that everybody believes except the person who made it. So this was a statement made by Einstein, and of course, nowadays you see, unless you do a DFT calculation, people will not believe it. But ours was a simpler calculation. Even though I had argument to convince people that even if you did a DFT calculation, the results will not be different. I was not successful. And then of course there is the question: is there any use in this? So we published the paper. I did not worry about use because I am not an expert in this. But anyway, there is shortly 1 year later a very interesting use was published. See, normally if you have a fluorescing moiety like rhodamine 60, then it is not possible to observe resonance Raman scattering from the molecule, because if you put it into solution and try to observe resonance Raman scattering, you get this appearance, this rather flat. It's not really flat, but you don't see any Raman scattering from the system. So these people had the idea, because we said that graphene is a very good acceptor. So they put rhodamine 60 in the vicinity of graphene and then again did the experiment. What graphene will do is, if you have an excited rhodamine 60, it will cause the excitation. And therefore there will not be any fluorescence. But on the other hand, Raman scattering is a very fast process, and the Raman scattering will take place even before the excitation is quenched. And therefore it will be possible to observe Raman scattering, resonance Raman spectra of rhodamine 60 if you put rhodamine 60 in the presence of graphene. And that experiment was done and published. Of course, I had nothing to do with this other than suggesting that graphene is a very efficient quencher. So this is the resonance Raman spectrum that was observed for rhodamine 60 in presence of graphene. Another interesting application was that, see, normally it was very difficult to locate where graphene is sitting on a silicon wafer. So what they did was, they took the wafer, deposited graphene, and then coated the entire thing with a dye. And then you shine light on it and the dye gets excited, but wherever graphene is there, the dye excited is quenched, and therefore there will be any fluorescence. But if you have no graphene beneath the neighborhood, then the dye will fluoresce, and therefore you can see, if you did this experiment, you will see that there are regions where there is no fluorescence. For example, here in this region there is fluorescence, but in this region there is no fluorescence. Why? Because there is graphene sitting beneath it, and therefore this was a technique to locate graphene on the surface. And this has actually been developed into something which is referred as fluorescence matching microscopy by the group of Jiaxing Huang. And that is again their work. It is just an application of what we predicted. Then people measured carefully the resistance dependency experimentally and found that this is the experimental curve published in 2013. And the external curve perfectly matches the experiment, and this is the result in 2013. Another experiment appeared last year where they used DNA origami nanopositioners to keep the dye molecule at well-defined distances from the graphene sheet and measure the rate of energy transfer. Again, they found a perfect 6 to the power of -4 dependence. And now if you go to Google and search for graphene FRET sensor, whenever you have fluorescence quenching, you have a potential sensor. So we had suggested that graphene is a very good quencher, and therefore people tried to use that. And so if you go and search for graphene FRET sensor, you will find lots of images, which are all essentially applications of our prediction. And we made another prediction. I realize I am running out of time. So let me try to finish up. So you see, this is the Q is equal to 0 excitation, and as I told you earlier, the Q is equal to 0 excitation, and the excitations in the neighborhood are the ones responsible for distance to the power of -4. But suppose somehow I can prevent this excitation from taking place. Then what will happen? Your distance dependence will change. So how can I prevent such excitations? The answer is that, you see, I take the Fermi level, all the levels up the Fermi level are occupied with 2 electrons, so therefore if I shift the Fermi level to a new position which is something like this, then what will happen? Such an excitation is not possible because the excited state is already populated with electrons. So by shifting the Fermi level, you can prevent excitations with small values of Q, and therefore what will happen? We did theoretical calculations and predicted that it will now behave like exponential in Z, which means that, you see, if this was the situation, energy will be transferred by if this was the situation, transfer will be very low. So therefore, if you had a fluorescing molecule and if you put it near graphene, it will not fluoresce because the excitation is quenched. But if you then apply a potential difference causing the Fermi level of graphene to shift, then you can make the molecule fluoresce because the graphene will not accept the excitation energy. And this was a prediction that we made. We did not think that it will be soon experimentally verified, but interestingly this has been experimentally verified. So normally it is a power law like the left-hand figure, but by shifting the Fermi level, it becomes exponential. So this was verified experimentally, again, which is the year, I think, 2014, it was experimentally verified. Okay, so they claim that they have a switch which can switch on and switch off fluorescence, and you can control light emission. Then we worried about energy transfer to nanotubes. The question is the same. From a dye, what will be the rate of energy transfer to a nanotube? As far as I know, there are no careful experimental measurements. What is the distance dependence? We did calculations and we predicted that it will be 1 by distance to the power of 5, and further the energy transfer can be observed up to 17 nanometers. As far as I know, there has not been yet any experimental verification. The experimental verification is not difficult. So here is a summary of what I presented for dye nanoparticle. The distance dependence we found is 10 to the power of -6. It is not distance to the power of -4. At short distances there are corrections, but plasmons and electron hole pairs do not give distance to the power of -4. It cannot be transferred through the DNA, it cannot be the asphericity of the nanoparticle, and in fact I am very happy to tell you that more detailed calculations have become available, not from our group but somebody else has done it, and their results are in agreement with our own results. In the case of digraphene, we predicted that the energy transfer is very efficient. It can take place up to 30 nanometers. This has been experimentally verified, the distance dependence has been experimentally verified, and another interesting thing is it is possible for one to switch on and switch off fluorescence. That again has been experimentally verified. In the case of dye nanotube, distance dependence is 1 by d to the power of 5. Experiments are needed, for example, an experiment where you would put the nanotube at the tip of an AFM. AFM tip, you put it and then excite it and study energy transfer. This kind of experiment. With the current technology, it is possible, but as far as I know, nobody has done it. And this is the papers that we published. And this is my student who is currently a faculty member in Trivandrum. Swadish did it very nicely in my group, and that brings me to the conclusion of this lecture. I want to thank all of you for listening, and I first would like to thank the Indian Chemical Society for giving me this wonderful opportunity to speak in memory of my former supervisor and my guru. I would like to thank you all for listening to me once again. Thank you.
Thank you, Professor Sebastian, for a wonderful lecture. I think we will continue with this program. Professor Sinha.
Yes, sir. Thank you,
Yeah.
Professor Srivastava. And I think Professor Mukherjee, DC Mukherjee has something to say.
Yes.
DC Mukherjee, sir, could you say? Hello, Professor DC Mukherjee. Mukherjee, sir.
His,
Sir, শুনতে পাচ্ছেন?
his microphone is muted.
Can you hear me now? Can you?
Yeah. Sir, just you mute your microphone.
Okay.
Yes.
Okay. So I am very much grateful to Professor Sebastian, and actually he is my boy. I have been the opportunity of becoming the first PhD student of Professor J.K. Chandra, and I am extremely grateful that Professor Sebastian has agreed to deliver this lecture. The renowned-
I would like to thank Professor Mukherjee, because he is the one who contacted me all the time and asked me. Thank you very much.
And I am a very lucky person, and I could initiate this endowment lecture, very humbled by my humble offering, and thus I was able to pay my tribute to the most respected teacher of mine, and I hope that we all together will carry the very fond memory of our common Guru, Professor A.K. Chandra. Thank you very much, Professor.
Thank you.
Thank you very much, Professor.
For information of the audience, I would say that this award, A.K. Chandra Memorial Award, is funded only contributed by Professor Mukherjee.
Oh, very good. Very good. Thank you. So, Professor Sinha, we
Yes,
have to
sir.
go for the next lecture, right?
Next lecture, Professor A.D. Khan from IIT Guwahati, PK Bose
Yes.
Memorial.
Yeah, so I will say a few words about him.
Yes, sir. Yes.
Okay.
So,
This is Professor P.K. Bose Memorial Award Lecture 2018, which will be delivered by Professor A.T. Khan, who obtained his post-graduation degree and thereafter PhD in 1990 from the University of Kalyani. And during his work, his PhD work, he worked with Professor K.C. Mujumdar and carried out his research on phase transfer catalyzed alkylation, which is very dear to me, signotrophic rearrangement and synthesis of heterocycles. Then he joined with Professor Govardhan Mehta in the School of Chemistry at the University of Hyderabad for his postdoctoral research, and he worked on the synthesis of natural products. He was awarded CSR Net, JRF, and as well as CSR RA for his postdoctoral work, Professor Mehta. He thereafter was awarded the prestigious Alexander von Humboldt Fellowship to pursue his second postdoctoral work with Richard Schmidt at the University of Constance, Germany. And then he worked on carbohydrate chemistry with total synthesis of natural products. After returning, he joined as scientist fellow in the natural products chemistry division in Surat. And later on, he started his independent academic work since 1996 as assistant professor at IIT Guwahati, and presently he's serving as the Hag professor since 2010. He has guided 25 PhDs and also published 142 plus research papers in various international journals, which deal with synthesis of biologically important molecules, heterocycles, carbohydrate chemistry, etc. He is an elected member of Indian National Academy of Indian National Science Academy, Nasi Allahabad, and fellow of Royal Society of Chemistry, UK, and Indian Chemical Society. He also has an administrative experience as a professor in charge of Faculty of Affairs and Dean of Faculty of Affairs in Indian Institute of Technology, Patna. He also served as the Vice Chancellor of Alia University in Calcutta on deputation. He is compassionate about his teaching and research as well as administration. So, Professor Khan, the podium is yours. Thank you so much.
Yeah. Settle. Good afternoon. I am extremely thankful to Professor J.D. Jadhav and Indian Chemical Society for giving this award to P.K. Bose Memorial Award. Can you listen my voice? Is it audible?
Yes, yes, your voice is audible. Please go ahead.
I am staring. Little difficulty is there. We'll finish start just within a minute.
আপনি কি করবেন? আমি বাড়িতে ঢুকেছি, আপনি আমাকে ঢুকিয়েছেন, আমি এখন যা খুলে রাখছি।
আরে এক্ষুনি তো আপনি বললেন তো ইয়ে নিতে পয়সা দিয়েছে কি করতে?
Is it sharing?
Yes. It is visible.
Visible. So I can go ahead. So the title of my talk is Exploration of Nitroalkene in Organic Synthesis and what we are doing last couple of years. And I am thankful all the Indian Council, Indian Chemical Society members, presidents, and today I have seen webinar. Many of my teachers are also online, particularly Professor Kalapatru, Professor Mukherjee, and many more, and we are thankful to all of them. So this is the picture of Professor P.K. Bose. I would like to say a few words about him. He stood BSc and MSc both first class pass from Calcutta University. In 1992 he completed his masters. Then he joined with Professor P.C. Ray as his PhD student and completed his thesis work 1933. And he is also recipient of Pilades Fellow, which is prestigious awarded to the student in Calcutta University. And later on he moved to, but most interesting thing is that he likes the chemistry of organosulfur compounds because he knows the sulfur has special use as medicine. And the medicinal plants, we know garlic, it has medicinal value. So he was fond of interest to do some medicinal plants where he can do research. Later he has a dream to work on natural products and started the school. And lastly his student, Mr. Chatterjee, has established Natural Product Chemistry Division in Calcutta University. This is short thing about Professor P.K. Bose. Before starting the conference, I would like to say a few words from Swami Vivekananda. What is the need of conference or symposium and colloquium? So if you read his statement, if we exchange 1 rupee, we both will have 1 rupee. If we exchange 1 good thought, we both will have 2 good thoughts. So he is one of the visionary person in India, Swami Vivekananda. I am very fond of him. So let us start my work, what we are doing and talking about it. See, nitroalkene has a versatile building block. Why? Because if you see it there, I have written that it is a electron deficient alkenes and it has can be used as Michael acceptors or as precursor of stabilized anions able to attack and electrophile as well as nucleophile. So it can see there is a alpha and beta carbon. This alpha carbon, beta carbon is electrophilicity is there, and nucleophilicity as the alpha carbon. So if you see the structures, so we can play around it. You can treat with nucleophile, so it can react with alpha carbon. It can react with beta carbon if you temporarily arrest this alpha carbon. Similarly, if you take nucleophile and electrophile, so both you can react with that. By taking this idea, these many reactions have been developed so far. One is familiar reaction, Michael reaction, one called azamichael, oxamichael, thiamichael reaction. Diels-Alder reaction, very famous, Morita-Hillman reactions, functional group manipulation, and Umpulan reactions. Many more reactions have been developed. I have found these are the most important for the student point of view. So I am to see where nitroalkene is used. The first one, you can remove this nitro group to make carbonyl by using NEP reactions. There is a nice chemical review article there. And you can react with aldehyde without masking the carbonyl, which is Umpulan strategy. You can do stator reaction, which is very popular. And then one more thing is that this looks like dienophile. It should be dienophile, but it can be used as Diels-Alder reactions, and it can be used as a Morita-Hillman reaction, which is a famous reaction from Sir Baswaya. And you can use as asymmetric Michael reaction, addition reactions. But this paper has unique that you can use the reaction in water, and you can use a super DMAP as catalyst to do the asymmetric Michael addition and the stereochemical defined air also. So with this idea, we are playing around because I was busy with administrative job. So most of the work has been done by the student. So best way to prepare nitroalkene, nitrostyrene. This is the two method which is we have noted, but earlier method is there, but this is the best method to prepare it as our one of the starting material. So this paper I have given you reference. You can see the student have an interest. This is a chiral amine. You can block enamine reaction, stop enamine, and then you can do the reaction with the Michael reaction for asymmetric reactions. And the catalyst, this is called super DMAP because 3 nitrogen is there, and block so that it can react with the alpha carbon and it can react to the beta center at the electrophile so that you can do the product. And another interesting that innovatable aldehyde you take, and then you can take keto, nitrostyrene, then you can get it. And similarly, this paper, this is a chiral catalyst, and stabilized by another 20 more percent chlorobenzoic acid, and then you can go Diels-Alder reaction. This paper is very interesting for the scientific community because if you see the mechanism, looks like how it can give Diels-Alder reaction. So this catalyst can react and it can give a enamine, and enamine looks like a dine, and that will react with dienophile with the nitrostyrene. And this is stabilized by the co-catalyst. If you interestingly you can see it, and then water is the medium. Finally, bicyclic 2-2 system can be generated having suitable functionality. So you may think that nitrocyanine is a dynamite and sometimes cyclohexanone also act as dynamite. Then how it is feasible to react to give Diels-Alder reaction? But with this literature things, we encourage and saw what we can do with the nitrostyrene. Many more paper has come. In between, the scenario of organic synthesis has dramatically changed. So multi-component reaction is one of the approach which is UD has given. So if you take nitrostyrene, aldehyde and this, so you can get many complicated, many functional group you can incorporate in the molecule. So what we have done is, if you see this is a pyrrole derivative, this is a highly substituted. Why we interested this? Because this is a highly substituted pyrrole. There is a drug called atorvastatin. Trade name is Lipitor, which is cholesterol lowering agent. This is exactly polysubstituted pyrrole, pentasubstituted pyrrole. Only difference is there. There is in R, here it is a aliphatic amine component is been derived. So what we have taken beta-ketoester, aldehyde, amine and nitromethane. So we have generated this nitromethane and aldehyde in situ, this nitrostyrene, and then we can prepare this pentasubstituted pyrrole. And this is a highly cited paper, and we have found, I am not going to discuss it, this compound is very useful. It is used as a potential phosphodiesterase 4B inhibitor, and we have done collaborative work. This molecule can be used for that, but experiment has to do for real to see the exact value of this. So many examples we have done it, if you can see it here. So some of the example reaction are good, but if you see in this structure, nowhere nitro molecule is involved in the molecule. So at the end, it has been knocked out. And I would like to say the mechanism if you see is quite interesting. This is generated because this is catalyst we have given name BDMS, which is discovered by Ola. Professor Bhankar has done quite work. Then that time he was doing postdoc. After that we have done around 50-55 papers. We use this BDMS. So you can see it here. This gives enamine, and nitromethane and aldehyde can react. We can give with nitrostyrene, and this nitrostyrene. So this is a imine and nitrostyrene can react, and ultimately it gives the product, and finally this nitro group is eliminated. But we can do all the position is functionalized. If you take instead of nitromethane, if we take nitroethane, then you can incorporate here ethyl group actually. And the interesting thing is that this is a 4-component reactions. You can get single spot all these compounds, and this is a highly rated papers. I think near about 66 Google citation has found. The next thing is that what we want to do is that this nitrostyrene has a Michael acceptor, and the 4-hydroxydithiocoumarine can give as a Michael C as a 1,4 addition, because this can enolate and it can react with this 3 position of 4-hydroxycoumarine to give this. But interestingly thing what happened, if you see it here, the literature procedure, if you see it, this compound making is very lengthy process, but our idea to make it to one heterocycle to convert to another heterocycle, which is expensive because this flavon moiety is being used, pricing is there, many compounds are already there, they are used as a drug. So we thought, can you convert cheapest compound 4-hydroxycoumarine to the flavon moiety? So we have seen lot of compound can be used for this purpose. It is giving many good result. But interesting thing, when we take alcohol, phenol instead of alcohol, reaction does not go. Amine if we take, secondary amine we take, the reaction is failure. So it is interesting how it works. So if you see 4-hydroxycoumarine react with nitrostyrene to gives 1,4-methyl product, this DMAP is opening up the lactone ring and it reacts, and then your alcohol is attacking to denocking the 4-methyl DMAP, and then finally cyclization occurs here and nitro group is eliminating. So nitromethane is nowhere in the molecule, so we are losing, and ultimately we are getting the flavone moiety. So you have seen that can be used as a 3-component reaction. So this is we use in MCR. Then the same molecule can be used to the aromatic compound. If you see it here, very interesting, that if you take malononitrile, nitrostyrene, aldehyde, again catalyst DMAP, but you get 2,3-diaryl 5,6, 2,3,5 disubstituted 2,6-dicyanoaniline derivatives, which is a very interesting molecule. So if you see it here, many literature procedure is there, but they got not selectivity, but in our case, we have obtained the best result. So many examples are there, I can show it here. So in mechanism is interesting, what is happening, the DMAP can react with malonitrile, so it can give an ion which can react with the aldehyde to give noble gel product. And this, on the other hand, this two-way it can react, this nitrostyrene